Welcome everybody to today's webinar about products of variables in mixed integer programming. Here's the outline of the webinar. So initially we start with introducing what is a mixed integer linear program. I guess everybody on the call should know this. And then we look at a different concept, which is mixed integer bilinear programs. And now from bilinear programming, there are several techniques that are used by today's solvers to improve performance on bilinear programs. And one of those techniques is the so-called McCormick relaxation that is used. And then on top of it, one can generate so-called RLT cuts. This is reformulation linearization technique cuts. And the goal of this webinar is to show you how one can apply the same technique also on mixed integer linear programs. But in order to do so, we first need to identify the structure in mixed integer linear programs that give rise to those products of variables. And then we can use these products of variables in order to separate RLT cuts and also another class of cutting planes, which will be explained later. So we exploit those product relations then for cutting planes, and then I will show you some computational results which demonstrate how effective those are to improve performance on mixed integer linear programs, but also on quadratic programs. So let's get started. Here is the definition of a mixed integer linear program that I will use today. So an MILP is defined as minimizing a linear objective function C transpose X such that certain linear constraints must hold. So A times X is smaller or equal to B. Of course, you can also use equations or larger or equal inequalities, but let's keep the standard form here right now. The variables X are non-negative. Of course, in general, you have lower bounds and upper bounds, but you can always transform all mixed integer linear programs into this standard form here. And some of the variables, namely those that are in this index set I, they should take integer values in the solution. And this is what makes the problem hard. So as you all know, this problem class has a very large number of applications. You can see here this list, which is not exhaustive. So there are many more, but this is what most of the users of Gurobi usually solve. And here is another class of problems that we are interested today, and this is called a mixed integer bilinear program. So this is almost the same as a mixed integer linear program, but here we have another set of variables that are called y here in the slide, which also have linear objective function coefficients d, and they also participate in the linear constraints with this coefficient matrix capital D. And then there are these so-called bilinear constraints that link the y variables to the original x variables in such a way that for a variable yij, this is defined to be equal to the product of variables xi times xj. Not all of those yij variables need to exist. So there is only a subset S, which contains the pairs of indices I and j, and only for those we have such a yij variable that is mapped to this product of xi times xj. And as before, the x variables should be non-negative, and some of them are integers. This problem class also has a large number of applications, most notably the pooling pop problem, which arises in the petrochemical industry. And you see here that there are a number of other applications as well. So that's an important problem as well. Until now, so until version Gurobi 8.1, we cannot solve this problem because those bilinear constraints are non-convex. But with the new version of Gurobi 9.0, we are actually able to solve this type of problem. So how are those problems being solved? So one possibility, and this is used by many of the solvers that are currently able to solve such problems, is to use the so-called McCormick relaxation. So we use, just like in MILP, an LP-based branch and cut approach to solve the mixed integer bilinear programs. And the LP relaxation of these bilinear constraints is given by these four constraints, which are called the McCormick relaxation. So you can see on the right-hand side, this saddle shape, that is the feasible set of a bilinear constraint. So you have x1 and x2 here, and then on the y-axis, you have the product of the two variables. So as you can see here, this is a non-convex set. And now if you look at those four inequalities, they form the convex hull of this set. In particular, you have these first two inequalities, which are the lower envelope. You can see this here on the picture on the right-hand side. These blue lines tell you what the constraints look like, so the hyperplanes that these constraints define. And of course, these constraints depend on the lower and the upper bounds of the variables that are involved. So Li, Ui, Lj, and Uj are the lower and upper bounds of Xi and Xj, respectively. And then the second set of constraints is the upper McCormick envelope, which are these other hyperplanes that you see here in the picture on the bottom. And now what you can see very clearly here is that what can happen and what will happen very often if you solve this LP relaxation is that you get an LP solution that is not on the surface, on the saddle surface here, but instead just inside this polyhedron that is given by these four constraints. And that means that such a bilinear constraint will often be violated by the current LP solution. So what can we do if an LP solution violates a constraint? Well, one possibility is to add a cutting plane that cuts off this infeasible LP solution. And this is what these so-called RLT cuts are about. So they are cuts that are derived from a more general technique that is called the reformulation linearization technique. And they work as follows. So given is a mixed integer bilinear program, as we have defined it before. And now we take some linear constraints, so it could be an equation or an inequality, and we multiply it by some non-negative variable xj. So of course, after multiplying by xj, the resulting constraint will be a quadratic constraint. And now we linearize the resulting quadratic constraint. So there are now two cases. So one is the product term xi xj that you get after multiplying by xj is actually part of our set S. So there is a variable yij that represents this product. In this case, we just replace this product by the yij variable, and then it is a linear term. The other case is that this product does not exist in S, so there is no yij variable that we can use. And in this case, we need to find a different way of linearizing it. For example, we could just replace the quadratic term with one of the McCormick underestimators. So question is, why can this be useful? So if we have a product relation, yij is equal to xi times xj, and this product relation is violated by the current LP solution, then it could be that replacing the xi xj product by the yij variable increases the activity of our constraint. And for this reason, it could be that the resulting linear constraint is violated by the current LP solution, and then it is a cutting plane. Okay, so now we want to go back to mixed integer linear programs. How can we use this technique of RLT cuts? So we somehow need to find those product relations also in mixed integer linear programs. Of course, they will not always exist, but sometimes they do exist. So namely, some products do not need to be explicitly stated as bilinear constraints. If one of the variables that is involved is binary, and the other variable can be binary or non-binary, then such a product can also be modeled using linear constraints. So that means such a product can actually appear in mixed integer linear programs. So if you look at these inequalities here, these are just the four McCormick inequalities that we have seen to linearize a quadratic constraint, yij is equal to xi times xj. And now we assume that the xi variable is binary. And that means here in these McCormick constraints, these coefficients Li and Ui, they are just 0 and 1 respectively. So if we just replace those coefficients by their corresponding values, then we get this set of inequalities. And now if you look at those in a bit more detail, then you see that they just model indicator constraints. So let's take the first constraint here as an example. This just says, if xi is equal to 0, then the yij variable has to be larger or equal to 0. On the other hand, if xi is equal to 1, then this first constraint says that the yij variable should be larger or equal to lj, to the lower bound of the xj. And now the second constraint says, if xi is equal to 1, then this uj coefficient cancels out with the right-hand side, and we just have that yij is larger or equal to xj. And if xi is 0, then this is a redundant constraint. So that means in total, these two constraints together say that yij is larger or equal to xi times xj. Okay, and the same holds true for the second set of constraints. So this just models the relation that yij is smaller or equal to xi times xj, and that means in total all four constraints state what we want, that yij is equal to the product of xi times xj. Okay, so we want to detect this set of four constraints in a general MILP formulation, because if we detect this, then we can say that this variable yij is equal to the product of xi times xj. And then in the next step, when we apply RLT cuts, we can exploit this. So how can we detect this structure? First, let me show you a little bit some very useful MILP data structures that we use all the time. So those are the implied bound table and the clique table. So what is an implied bound? So an implied bound is a relation between a binary and a non-binary variable, namely that if you fix the binary variable to some value, say for example 0, that then the non-binary variable has a certain bound. So in the first example here, that xj is smaller or equal to b. So xi equals 0 implies xj smaller or equal to b. That is one implication that can be stored in the implied bound table. And then there are, of course, all the other possibilities. Variable can be fixed to 1, and we can also have larger or equal, so lower bounds for the implied variable. Now, a special case is that the second variable, the xj, the implied variable, is also binary. In this case, such relations are not stored in the implied bound table, but instead they are stored in the clique table, because in the clique table, one can store them much more compactly. So if you have, let's look at the first example again here. If you have a binary variable that is fixed to 0, that implies that a second binary variable is also fixed to 0, then this corresponds to this constraint minus xi plus xj smaller or equal to 0. And then we have the other three cases analogously. And now with the cliques, you have the situation that you can store many of those implications in a single linear inequality. So consider this graph here. This is why this is called a clique, right? Because this graph is a complete graph, so a clique, where each pair of nodes have an implication between them. So a relation that at most one of the two can be set to 1 in any feasible solution. And such implications you can easily store with a single constraint. Here in this case, the sum over x1 through x5 is smaller or equal to 1. So this single constraint corresponds to all of the pairwise implications. So that is a quadratic number of implications that you can represent by a single inequality here. So these are the two data structures that we deal with all the time in MILP solving, and that will now also be useful for detecting products in mixed integer linear programs. In Gurobi, we actually detected a little bit more general version of products. So namely, we want to detect such pairs of implications, namely that if a binary variable is equal to 1, then this implies that a non-binary variable yij is smaller or equal to some a times xj plus b. And the other implication of this pair is that if the binary variable xi is equal to 0, then the same variable yij is smaller or equal to a affine linear constraint of the same variable xj. And if you translate these indicator constraints into linear constraints, then you see this big M formulation that you have here on the right-hand side, with the big M chosen large enough such that the constraint becomes redundant if the xi variable is set to the opposite value. So those are the constraints that we want to find. So how can we detect these structures in an MILP formulation? So what we do is we start with an inequality with exactly 3 variables from which at least one of them is binary. So we just go through all of our constraints. Whenever there's a constraint that has length 3 and has at least one binary variable, then this is one candidate to start with. And now for each of the binary variables, so there can be more than one in this constraint, we just assume that this is our xi variable, and then we search for the other constraint in the remaining constraint system. And now there are several cases that we need to consider. So the first case is that the second constraint has actually a non-zero coefficient for our xj variable. So the c is not equal to 0. In this case, we are looking also for a 3 variable constraint with exactly the same variables, xi, xj, and yij. So then there is the case that the c is actually equal to 0. So the xj does not appear in the second constraint. In this case, the second constraint is an implied bound if yij is non-binary, or a clique if yij is binary. So this we can find in our tables that we have just discussed. And the third case is that also the big M here is 0, so that means also the xi does not appear in the constraint. Well, then this is a trivial constraint just on the yij, so which is just a global upper bound on the yij. This we can easily look up in our upper bound vector. Okay, if we have found such a second constraint that matches the first constraint, then we have found this relation that you see here below, namely that the yij is smaller or equal if xi is 1, then it's a times xj plus b, and if xi is 0, then it is c times xj plus d. So, and if you multiply this through, then you get that this is smaller or equal to a minus c times xi xj plus b minus d times xi plus c xj plus d. This whole thing is only interesting to us if a is not equal to c, so that means there is a non-zero coefficient in front of this product term xi xj. And if this is the case, then we just divide by a minus c, move everything to the left-hand side and keep the xi xj on the right-hand side, or the other way around, and then we have a product relation with the xi xj product on one side and an affine linear term on the right-hand side. And this is what we store in our product relation table. Okay, some more details, because detection is quite involved and it is not so easy to make sure that this is fast in practice. So I'd like to talk a little bit about the tricks to make it fast. So as I said, the basic algorithm is to first find all the implied relations by scanning the length 3 constraints with at least one binary variable. Those are stored in an intermediate table, an implied relation table. And now for each of these implied relations, we try to find this other constraint, so the matching constraint to form this pair. So, and this can be another implied relation, so that would be another length 3 constraint, which is easy to find because we can just apply binary search for this triple of variables in our implied relations table that we have sorted lexicographically by these 3 variables. Then the second case is that this c is equal to 0, so we are looking for an implied bound. And this means that we have to apply a linear scan in our implications table, which can be expensive, right? Because if we do this linear scan for every length 3 constraint that we have, then this is kind of the runtime is the product of the number of length 3 constraints and the number of implications. So one has to be careful a little bit, but in practice, this was never a bottleneck here. Second alternative, if C is equal to 0, is that Yij is actually binary, and then we have to scan the clique table instead. So Gurobi stores the clique table not only in a row-wise fashion, so that means for every clique we know which are the members of the clique, but it also stores it in the column-wise fashion, so that means for every variable Yij or its complement, Yij bar, we know in which cliques this literal appears. So now we are looking for a clique in which both Xij and Yij and Xi appear. So that means we just need to scan these two columns and look for a matching clique index. That should be fast as well. And then there is the case of an unconditional relation. So it could be that we have a clique implied bound on length 2 inequalities for the Xj and Yij variable, or a global bound of Yij. So all of this can be found relatively quickly by using a mix of hashing, binary search, sorting, and stuff like that. Okay, and after having found this, we also try to find constraints in the opposite direction, because if we find these sets of constraints in both directions, then we have actually found an equality product relation, which is very useful in practice. There is another special case that I want to quickly mention, namely, it could be that you have a product relation that is defined by linear constraints without any length 3 constraint. So that means our basic algorithm would fail because it needs a length 3 constraint to start with. So it could be, in here, this is an example that the product relation is given by an unconditional relation, in this case, this Yij smaller or equal to A times Xj plus D, and an implied bound constraint, so that the binary Xi equals 0, for example, implies that the Yij is smaller or equal to D. And this also yields such a product relation that you can see here. Question is, how can we detect it? Because we don't have any length 3 constraint to start with. So, but we can start with our implied bounds that we have stored in our implied bound tables. And this is what we do. The problem here is just that if we only have an implied bound, we only know 2 out of the 3 variables that we are looking for. So that makes the detection algorithm a little bit more complicated. We could also start with our cliques, because they also define length 2 relations between variables. But this we don't do, because in a clique table, each clique represents a quadratic number of such length 2 implications. So that would be way too many in practice to make it efficient. Okay, now we have detected all of these products in our linear constraints. And now we are going to use these products in order to separate these RLT cuts. Okay, how does the separation algorithm work? So we start with a variable xj, and this is the variable that we want to multiply to the constraints. So because we need to multiply the constraints with a non-negative value, that means we have 2 choices. One is xj minus lj, and the other one is uj minus xj. So lj being the lower and uj being the upper bound of the variable. So we just try both. And now we ask ourselves again, why can this lead to a violated cut in the end? Well, the reason is, as I have said initially, that this product relation, Yij equals to Xi Xj, or Yij smaller equal to Xi Xj, or larger equal to Xi Xj, is violated by the current LP solution. So what we are now looking at are the product relations between Yij and Xi Xj that are violated by our current LP solution. And now we are looking at these 2 variables, Xi and Xj, and just pick one of the 2, say Xj. And now we mark all the constraints in which Xi appears, right? Because such a constraint in which Xi appears if you multiply this constraint with xj, then you get this product xi xj, which you can then replace by the yij variable. And there you have the violation from the relaxation. So this could potentially lead to a violated RLT cut. Problem is, we also need to look at the sign of the coefficient of AI, because the violation of our product relation is in one direction, and it only makes sense if this violation and the sense of the product relation corresponds to the sign of the AI, so that this matches. We have collected all the constraints that we want to multiply with xj, and now we multiply each of these constraints by xj minus lj or by uj minus xj. And this yields a quadratic constraint, as we have seen before. And then we just do the usual thing that we have already seen for the general RLT cut framework. Namely, we have to substitute these product terms, xi, xj, using our known product relation or a linear relaxation. And this is the important step that I will show you on the next slide. So substitution. We have multiplied our constraint by xj, so we get all those product terms xi, xj. And we have to get rid of them by replacing them with a linear term. Now there are several cases that we can consider. So let's assume that the I is actually equal to the j. So we have multiplied a constraint in which xj appears by xj, which gives us a square term, so xj squared. And if xj is a binary variable, then the situation is very simple, because for binary variables xj, it just holds that xj square is equal to xj, right? Because 0 square is 0 and 1 square is 1. So we can just replace the xj square by xj in this case, and the term is linear. Now let's assume the xj is non-binary and we have a square term. Now it depends on the sign of the coefficient, so aj in this constraint. If this coefficient is non-negative, then we are in the good case, because then this term here is convex, and we can just linearize it by adding a tangent to this quadratic term here. And we use the tangent exactly at that point where our current LP solution is. That means the tangent in the current LP solution has exactly the same value as the quadratic term, which means that in terms of activity of the resulting cutting plane, we don't lose anything. Now the bad case is if the coefficient is negative, so aj is smaller than 0. In this case, the quadratic term is concave. And the only thing that we can do here is to use the secant, which depends on the bounds of this variable, right? So we need to find an underestimator of our term. So the only possibility here is the secant, and this we have to do. And here it could very well be that we lose activity of our cutting plane, which then may lead to an inequality that is no longer violated by the current LP solution. Okay, so now the other case is that we really have an xi and xj that are different. So I is not equal to j. Again, several cases we can consider. So first case is both variables are binary. And now assume that there is a clique in which both variables appear. Consider the first example here, that both appear with their positive literal in the clique. So that means xi plus xj is smaller or equal to 1. So that's our clique. And now it is very easy to see that the product of these two variables will always be 0. So that means we can just replace xi times xj with 0 in this case. And similar things hold for the other cases in which one or both variables appear with their complemented case, so their negative literal in the clique. So say this second row here as an example. So xi plus the complement of xj is smaller or equal to 1. In this case, it's easy to see that the product of xi times xj is always equal to xi. Okay, so this is the case in which both are binary and are part of a common clique. Now let's consider the case if one of the variable is binary and the other one is non-binary. So now we are in the case that we were talking about on the previous slides, that they could potentially be part of such a product relation. And also, if both variables are non-binary, it could be that if we are in the case of mixed integer bilinear constraints, that there is a bilinear constraint that links these two variables xi, xj to some variable yij. So in both cases, we can replace our xi, xj term by the corresponding yij variable. And this will, of course, appear at least once for our constraint because we selected the variable xj and this constraint in such a way that this term xi, xj appears, for which we do have a yij variable. Okay, and then there is this else case, as always, nothing applies. So we have to fall back to a regular McCormick relaxation here. If the coefficient is positive of our product term xi, xj, then we need to pick one of the two lower envelope constraints. If it's negative, then we need to pick one of the two upper envelope constraints. Here we have a choice because we have two constraints, and we just pick the one that is tighter at the current LP solution. Okay, now we have replaced all the product terms by linear expressions. So that means the resulting constraint is a linear constraint, and this one we can add as a cutting plane to the MILP solver. Of course, there's always the question, how expensive is it to separate these cutting planes? And for these RLT cuts, the very nice thing is that there is one trick to really speed it up. And here's the observation. If you look at the McCormick inequalities, how they relate to this saddle area that is defined by the bilinear constraint, then you see that at the boundaries, so if you have this rectangular shape here, and one of the two variables, x1 or x2, is at one of its bounds, then you see that the McCormick relaxation is actually identical to the bilinear constraint surface. In other words, this means that in the LP relaxation, if at least one of the two variables is at a bound, then there is no way that the corresponding McCormick relaxation solution can violate the bilinear constraint. And that means if we are looking for violated cutting planes that are formed by exploiting violated bilinear constraints, we only need to look at variables that are not at one of their bounds, so that are strictly between their bounds. So that means we can check the violation of the resulting cut on this projected system, where we only look at variables that are between the two bounds. And if we have found a violated cut on this small system, then we just repeat the whole substitution procedure on the full constraint in order to get a violated cut for the full system. Nice thing about Gurobi's approach here, and which is also very common with other solvers, is that we solve the LP relaxations using the simplex algorithm. And the simplex algorithm has the nice property that most of the variables will be at one of their bounds in any of the optimal LP solutions, because all of the non-basic variables are at their bounds. Only the basic variables can be away from their bounds. And that means we, most of the time, can work on a much smaller system here. Okay, then there is a second trick that might be specific to Gurobi. Namely, the RLT cut separator is often finding many violated RLT cuts and adding all of these cuts directly to the solver's cut pool would be just too much. So then the subsequent algorithm that would go through all the cuts in the cut pool and check for violation and so forth would just slow down too much. So this we need to avoid. In order to do this, we first add these violated RLT cuts to a local temporary cut table. And then we apply our regular cut filtering algorithm to this local cut table, which filters cuts based on violation and orthogonality. And only the cuts that survive this filtering, they will then be added to the global cut table, where they will then be filtered again together with all the other cuts. Okay, this is about RLT cuts. And now we are looking at a second class of cutting planes that Gurobi is separating in its new version 9.0, which are the so-called BQP cuts. So these are cuts that come from the Boolean quadratic polytope. Okay, so what is this? The Boolean quadratic polytope of dimension n is defined in a space of variables x, y, with x being n-dimensional and y being n² dimensional. And the Boolean quadratic polytope are those vectors for which each yij is equal to xi times xj for all of the ij's, and the xj's are binary. And of course, the polytope here now is the convex hull of these integer points. Okay, so that's an interesting polytope. One interesting aspect is that this is actually equivalent to the cut polytope. So if you want to solve max cut problems, then you can also solve an equivalent Boolean quadratic problem. Now there is a second interesting object here, which is not a polytope anymore, which comes from quadratic programming with box constraints. So what is this? So QPB here. No, same letters, different order. Dimension n, again, we have variables x, y, x being n-dimensional, y being n² dimensional. And we have the same constraints, namely that the yij should be equal to the xi times xj for all the ij's. But now we don't have binary variables, but we have continuous variables between 0 and 1. So that means this is actually the continuous relaxation of the Boolean quadratic polytope. And now we have a very important theorem by Bura and Ledgeford from 2008 that states that every valid inequality for the Boolean quadratic polytope is also valid for the quadratic programming with box constraints object that we have seen here. And this is surprising somehow, because the QPB is a continuous relaxation of the BQP. So that means in linear terms, it's always the other way around, right? That the constraints for the continuous relaxation are valid for the integer polytope, but here it's the other way around, that the cutting plane or the valid constraints for the BQP are actually also valid for this continuous object. Okay, so what does it mean? It means that every facet that we find for the Boolean quadratic polytope can be used as a cutting plane for bilinear constraints with bounded variables, right? Because if you have a bilinear constraint on bounded variables, then you can easily scale these variables that they are between 0 and 1. Then you can look for violated facets of the Boolean quadratic polytope, and those can then be added as cutting planes to our problem. So Manfred Padberg studied those facets of the Boolean quadratic polytope and starting in 1989, and he has written a large number of interesting papers on this. So, and some of the facets that exist for this polytope are the RLT inequalities that we have seen before. Then there is a group of facets that is called a PSD inequality. So this comes from positive semi-definiteness of some object. Then there are cutting planes called Clique and Cut inequalities, which are also facets. And then Yajima and Fuji in 1998 generalized these Clique and Cut inequalities to a more general class of facets, which they call the cut type inequalities. So all of those inequalities can potentially be used as cutting planes for bilinear programs. And as a first thing, what we currently just do is to look at these clique inequalities. Theorem of Pathberg says that if you have any subset S of the index set that has at least 3 elements, and you have any integer number between 1 and the cardinality of S minus 2, then this clique inequality here that you see here on the slide is valid and facet defined. So if you just look at the very simple case with alpha being equal to 1 and the set S have a cardinality of 3, then these inequalities are called triangle inequalities. And those triangle inequalities you can actually also infer as zero half cuts from the linear constraints that are the McCormick relaxation again of your bilinear constraints. So here pick these 3 constraints that you see here. Each of them model one of the inequalities, namely that if both variables xi and xj is equal to 1, then the corresponding yij variable needs to be 1 as well. If you add up these 3 constraints, then you get coefficients 2 for all the x variables, a coefficient of -1 for the y's, and the right-hand side of 3. Now you can divide it by 2. You get coefficients of 1 for the x, coefficient of -0.5 for the y's, and the right-hand side of 1.5. So then you round down the fractional coefficients of the y's to -1, and you round down the right-hand side to 1, and that's your zero half cut, which is exactly the triangle inequality. Okay, and these triangle inequalities are also facet defining for the BQP, even if S is not a maximal clique. Okay, these are the inequalities that Gurobi separates in the version 9.0. You have here the first inequality that we have seen on the previous slide. All the other inequalities you can easily get from the first one by just using the concept of switching. So this is nothing else than complementing the x variable and then applying the associated changes also to the definitions of the y variables. So using switching, we get actually 4 triangle inequalities, these 4 that you can see here. And how do we separate them? Well, this is really trivial. We just enumerate all the triangles that we get in our product relation table, right? So the yij variables form edges in our graph, and then we get triangles in this graph. We enumerate all those triangles and check whether the corresponding triangle cut is violated, and if so, we add these as cutting plane. And again, we could separate lots of them in many cases, so we first have to add them to a local cut pool, filter this local cut pool, and only add the surviving cuts to the global cut pool of Gurobi. Okay, so doing this, adding these RLT cut separation and the BQP cut separation on top of this detection of the product relations, then we see here this behavior of the solver in terms of number of search tree nodes. So you see here that by adding these cutting planes, the number of search tree nodes goes down. So by like 3, 4, 5%. For MILPs, we also can apply this for MIQP, so this is linear constraints and quadratic objectives, or MIQCPs, which is quadratic constraints and also potentially quadratic objective, and also for these non-convex MIQCPs, which Gurobi 9.0 can deal with, but not Gurobi 8.1. So search tree gets smaller. So what does it mean for the solution time? This is the next slide here. It also goes down a little bit, so pretty dramatic speed up for the non-convex problems, but also a significant speed up for the quadratic problems and also for the linear problems. We always define several subsets of our test set depending on the run times. So that means some kind of the hardness of the problem. So the dark blue bars on the very left bars for each problem class, those are all of the problems. So for MILP, you see this would be these 3,900 models. And if you go to the right in each category, then the problems get harder and harder. What we usually look at for speed up numbers is this larger equal 10 seconds or 100 seconds brackets. If you look at the 10-second bracket that you see here, that we get a 1.6% speed up for MILPs, an 8% speed up for problems with quadratic objective, 1% for the quadratic constraint, and a 70% speed up for the non-convex problems here. So for those, this is really essential. Of course, this is also where the technique comes from, but we can also find a nice speed up for the MILPs. And this is the end of today's webinar. So, and I'd thank you again for attending. And I'm now trying to answer some of your questions.